In our last class, we have seen that photoelectric effect, and we also discussed about the black body radiation, where we have seen that that light as a particle, and according to Planck, we are getting an equation, famous equation, that is A is equal to H nu, energy is equal to H into nu, where H is the Planck constant and nu is the frequency of the light. Now, in this class, we will discuss about the Compton effect, and before going to this topic, we will try to find out the unit of age. This unit of age, that is unit of age, I prefer to represent in this form, is equal to unit of E divided by unit of frequency. This unit of age, that is purely kinetic energy, that is equal to half into m into v square, that give you m into L square divided by t square. We are representing in the form of m is equal to mass, L is your length, and t is your time, divided by the unit of frequency, that is 1 by t, that gives you m into L square divided by t. That means m into L divided by t. So that's equal to, this is the unit of distance or r, and unit of these things m L by t, that is equal to momentum. M into L by t is a v, so that's give you the m into v, that's the momentum. So this is unit of momentum, that is unit of age, that is equal to unit of distance, that is your distance, and this is your unit of momentum. That means, look, this unit of distance and unit of momentum, that's give you the unit of angular momentum. That gives you the unit of angular momentum. So that means unit of age is equal to unit equivalent to or equal to the unit of angular momentum. That's why we have seen that the spin half electron having angular momentum is equal to half into h cross. You know that. That's related to the age. So age gives you the angular momentum. Now my question is, if a particle of mass m, it is possible, or is it possible to find out the length associated with this mass m? Is it possible to find out the wavelength or length, not wavelength, length associated to it? Yes, the answer is yes. We can find out the length associated with this. How? This age is equal to, we know that r into p, or r distance is equal to r distance is equal to, you can write that is age by p, that is equal to age by m into c. Look, this is the mass of the particle. If you only know the mass of a particle, you can evaluate the length associated to it, because the c and h, this is the natural constant, c is the velocity of the light, h is the Planck constant. We know this data, so we can find out the length associated with it, and this amount or this h by mc is known as a Compton length. Later we will see that this amount gives you the Compton length. I want to remember you that this Compton length is not equal to the de Broglie wavelength. This Compton length does not equal to the de Broglie. De Broglie wavelength and Compton wavelength is different from each other. De Broglie wavelength does not equal to the de Broglie wavelength. Look. So my next question is, what is the wavelength of a photon if it is having a same amount of energy with the electron? When electron is at rest, what is the energy of a photon? Next question is, suppose question is, what is the wavelength? What is the wavelength of a photon whose energy is the equal with particle in particle of rest mass m. So the question is, what is the wavelength of a photon whose energy is equal to the rest mass of a particle? We know that according to Einstein, this energy of a particle having mass m, the energy is E equal to mc square. This is the energy of a particle at rest. That is the energy of a particle. That should be equal to the, according to our question, that should be equal to the h nu, because we know that the energy of a photon is equal to h nu. So mc square, that should be equal to h nu. That means h into nu is equal to your c by lambda, or lambda is equal to hc by mc square. That's give you h by m into c. Look, this is how we previously proved that this quantity gives you the length associated to any particle. For any particle, we can find out the length associated to it. Whether it is gives you the wave or not, that depends on the particle size or mass of the particle. But every particle have a length associated to it. So this h by mc gives you the length associated with this photon. Now we are trying to calculate the length of this length. We know that this is the our Compton length represented by the LC. Literally, this LC is represented as a Compton length. Now we are trying to find out the Compton length for the electron. What is the Compton length for the electron? The next question is, so this is the length for the photon. What is the Compton length for the electron? So what will be the Compton length for electron? We know that L of C is equal to H into M into C, or we can write more purely that mass of electron into C, or if you write this A, 2 pi into H cross into C divided by mass of electron into C square, that is this thing is equal to these things, where this H cross is equal to your H by 2 pi. So H by 2 pi, 2 by 2 pi cut out, so this gives you the CC cut out, this gives you the H by M into C. Okay. Now in our previous class we told that 2 pi, this amount of the value of H cross into C, that is equal to 197.33 mega electron volt into Fermi femtometer divided by mass of electron into C square. This amount is equal to 0.511 mega electron volt. Fine. So this whole data gives you that this quantity will be, you can check in your calculator, 2426 femtometer. Look, the Compton wavelength associated with the electron of one electron is equal to 2426 femtometer, which is far more greater than that of the size of a nucleus. For one particle size, the nucleus size, we know that generally it is 5 to 6 femtometer. The first Bohr radius of a particle is near about 50 femtometer. So this quantity, this value is far more greater than that of the size of a nucleus. If size of a 200 particle, it will be little bit greater than the 5 to 6 femtometer, that will maybe 10 to 15 femtometer, but still this quantity is far more bigger. Now at that time the problem is, if a high energetic radiation fall on a particle, suppose an electron at rest, then it is scattered after fall on the electron. If a high energetic radiation, suppose X-ray, suppose this is a X-ray source of X-ray fall on a electron which is at rest, so it is scattered after falling on it. It is scattered. Suppose this direction is your X direction, this direction is your Y direction, so electron is recoiling. Recoiling electron, and this is your scattered photon, which is making an angle theta with this X direction, and this is making an angle phi with this X direction. This is your X-ray. Now at the year of 1923, after solving all the problem of photoelectric effect backward radiation, where Einstein and Planck already established that light is not only a wave, it's also a particle. They already established this thing. So after this solution of this problem, another problem is created, that is the when high energetic radiation having suppose wavelength lambda 1 fall on a particle or fall on an electron, and after colliding with the electron, it is scattered with a different wavelength, suppose lambda 2. And they saw that this lambda 2 is greater than lambda 1, that is wavelength of the scattered photon is greater than the wavelength of the incident photon. So this phenomenon cannot be explained with using the classical theory. What classical theory says? Classical theory says that if a light fall on a particle, so the scattered light, if a light fall on an electron, so as this is a very high energy radiation, and the electron which is bind. Now taking a natural example, suppose this is a suppose these things, suppose this is a carbon foil, suppose this is a extra source of molybdenum, this is a carbon foil. After falling the X-ray on the carbon foil, it is scattered. According to the classical theory, this scattered radiation having the same wavelength with the incident radiation. And number two, the intensity of the scattered radiation is proportional. The scattered radiation is proportional to the intensity of the incident radiation. That means, according to the classical theory, number one, the scattered radiation the same wavelength with the incident radiation. And number 2, the intensity of the scattered radiation scattered radiation is proportional to the intensity of the intensity of incident radiation. Fine. That means look, the electron at the carbon foil is, when high energetic X-ray fall on the carbon foil, the electron does not have that much amount of energy to absorb all the energy of the X-ray that is fall on it. So it will oscillate and creating an oscillating electric field. So after certain time it will radiate, and the radiation will be the same wavelength whatever the wavelength of the incident radiation, that is the X-ray. That is the according to the classical theory. And this radiation, the intensity of this scattered radiation have the same intensity, or intensity is proportional. This intensity of the scattered radiation, if it is intensity of the incident radiation, this I should be proportional to the I0 according to the classical theory. But if you see this phenomena experimentally, this theory is violated. What do we see? We see that this scattered radiation having different wavelength with the incident radiation. The wavelength of the scattered radiation is increases with respect to the wavelength of the incident radiation. So we can't explain with this classical theory. Now to explain this theory, it was Compton in the year of 1924. He explained considering the light or radiation as a particle nature, and very beautifully explained this phenomenon. Now we will tell what is the experimental thing, and later on what is the explanation given by the Compton, and that is the Compton effect. What is that? What is that? Suppose a source of light, source of X-ray, where X-ray is generating, fall on an electron. Suppose electron at rest. After fall on it, it is scattered. Electron is scattered. Suppose this is your recoiling electron. This is suppose your y-axis. This is suppose your x-axis, and this is your suppose scattered photon. Making an angle with the x-axis suppose theta, and this is making an angle suppose with the x-axis suppose this is phi. Suppose the energy of the X-ray, this is your X-ray, energy of the X-ray is E, and momentum of the X-ray P, that is equal to h nu by c. The scattered photon having energy that is equal to E dash. Suppose this E dash is equal to, obviously this E dash is equal to h into nu dash. This energy E equal to h nu, and momentum P dash is equal to h nu dash by c. And this recoiling electron having energy E dash and momentum suppose P dash, and this electron at rest having energy suppose E. Now according to Compton, this phenomena is we are getting experimentally. According to Compton telling that this X-ray is composed of stream of particle. He considering this X-ray wave as a particle. When this particle fall or collide on a particle, that is electron, so it's considered is a particle-particle collision. So if it is a particle-particle collision, and he also considered this particle-particle collision as an elastic type collision. That means elastic type, when we will say a collision as an elastic type collision, if the energy before and after the collision is same, remains same. Not only energy, the momentum before and after the collision will be same. That type of collision we can tell as a elastic type collision. So now this collision is, according to Compton, this collision is elastic type collision. So according to Compton, this collision is elastic type collision. What is elastic type collision? We already explained this. Now explain all this phenomena. As the space is too short, that's why we have to erase all these things. Look. So the momentum also concept and the energy also concept. So number one, conservation of momentum. That means before and after the collision, the momentum will be same. Before the collision, the momentum of the photon is p. And momentum of the photon is 0 because the electron is at rest. If it is at rest, the velocity of the electron is 0. If the velocity of the electron is 0, then the momentum of the electron is 0. So the momentum of the photon is only the momentum of the photon. So this is a p. That should be equal to the momentum of the electron. The recoiling electron, that is Pe, plus momentum of the scattered photon. In this side we are writing the picture. That is the X-ray coming this. Here is your electron at rest. This is the scattered or recoiling electron. And this is suppose your y-axis. This is suppose your x-axis. This is suppose your scattered photon. This is your X-ray source. This is your X-ray. This angle is your theta. This angle is your phi. Look, or Pe, that is momentum of the electron, recoiling electron. That is equal to momentum of the photon minus momentum of the scattered photon. Or if you square it, it's Pe square, that is equal to P minus square. You can write as, or this is A minus B whole square formula. What we can get? That is P square plus P dash square minus 2 into P dash into, what will be that? As the momentum is a vector quantity, so there will be a dot product. So that should be multiplied by the cos theta, because this source are going. The X-ray is going into the direction of x-axis, positive x-axis direction, and after scattered it is going into this direction and making an angle theta with the x-axis. So there will be a dot product between this momentum and this momentum, that is P and P dash. This momentum having P dash and this photon having momentum going into this direction. This momentum is P. This momentum is P. So as this is a vector quantity, so there should be a dot product multiplied by cos theta, or Pe square, that is equal to this P, that is the momentum of this photon, that is equal to h nu by c whole square plus P dash, that is the momentum of the scattered photon, that is h nu dash by c, that whole square minus 2 into h nu by c into h nu dash by c multiplied by cos theta. That means if you common h square by c square, that's give you the nu square plus nu dash square minus 2 into h square by c square into nu dash into cos theta, right? So suppose this equation is number 1 equation. Equation number 1. So this is your P square is equal to these things. This is equation number 1. Now second thing is conservation of energy, because this is a elastic type collision. So for this elastic type collision, we will consider the energy momentum will be conserved before and after the collision. So conservation of energy. What is that? So before the collision, the energy of the photon, suppose E, plus energy of the electron, that is E of E, that should be equal to the energy of the scattered photon, that is E dash, plus energy of the recoiling electron, that is these things. Fine. Or this E equal to h nu plus this E, that is energy of this electron at rest, that should be equal to m0 into c square, is equal to this energy of the scattered photon, that should be h into h nu dash plus this energy of the recoil energy. Look, this is the recoiling energy. After collision it is scattered. After collision it is recoiling. That means you have to use the relativity theory. So this energy should be root over P square c square plus m0 square into c to the 4. If you are not understanding this portion, you can write in comment section. I will explain this. We are getting the equation from the relativity theory of Einstein. That is E square is equal to P square into c square plus m0 square into c to the 4. These things. From the relativity theory, we know this equation. That's why I am putting these relations. So, or if you taking this side, this portion, h into nu minus nu dash plus m0 into c square, that's give you root over of p square into c square plus m0 square into c to the 4. So, these things. Or if you square it at the both sides, so that is h into nu minus nu dash plus m0 into c square, that is equal to root over of p square into c square plus m0 into c to the 4. So if you square at the both sides, square it at the both sides. So what we will get? Or this portion, that is, consider this portion is A, this portion is B. So A square, A plus B whole square relationship. So this gives you h into simply nu minus nu dash, that is square, plus m0 into c square plus 2 into h into nu minus nu dash into m0 into c square, that's equal to p square into c square plus m0 into c to the 4. Look, you know that the value of p square is equal to this thing. So put this equation here. So that's give you, that is equal to, look, this p square multiplied by the c square. If this c square is multiplied this equation, then we will get, that is h square into nu square plus nu dash square minus 2 into h square into nu dash into cos theta plus this quantity, that is m0 into, this is m0 into this will be m0 square into c to the 4. m0 square into c to the 4. This is fine. In previous time you checked once this. This is m0 square into c to the 4. This will be m0 square into c to the 4. Huh? So these things, or come this left hand side, or this is your h square into, if you look, a minus b whole square, that means h square nu dot square plus nu dash square, nu square plus nu dash square minus 2 into nu dash into nu dash plus m0 square into c to the power 4 plus 2h into nu minus nu dash into m0 into c square, that's equal to this whole thing, that is h square into nu square plus nu dash square minus 2 into h square nu into nu dash into cos theta plus m0 square into c to the 4. Look, this m0 square into c to the 4, m0 square into c to the 4. So this will cut out this portion. This portion will cut out. Everything is okay. And this space is very short, that's why the problem is arises. Or look, this h square into nu square plus h square into nu dot square, this portion also cut out. So remaining portion is minus h square into minus 2 into h square nu into nu dash, that's plus 2 into h nu minus nu dash into m0 into c square, that's equal to minus 2 into h square nu into nu dash into cos theta. These things, anything else? 2 into h nu minus nu dash m0 into c square minus 2h square nu into nu dash into cos theta. These things. Or that means get this form at the side. So that is 2h nu minus nu dash into m0 into c square, that's equal to, if you taking this part, this, that is 2 into h square nu into nu dash minus 2 into h square nu into nu dash into cos theta. Or look, this 2 is cut out at the both sides of this equation, and if you cross this h, this h, when you cut out it, so if you taking count, that is h into nu dash, that's give you the 1 minus cos theta, or nu minus nu dash is equal to h into nu dash divided by m0 into c square into 1 minus cos theta, or nu into nu dash, taking in this side, nu by nu into nu dash minus nu dash by nu into nu dash, that is equal to h by m0 into c square into 1 minus cos theta. That means finally we are coming, or this gives you 1 by nu dash minus 1 by nu, that's is the h by m0 into c square into 1 minus cos theta. So, or if once he is taking at the side, that is c by nu dash c into 1 by nu dash into nu, that is equal to h by m0 into c into 1 minus cos theta. Or that is c by nu dash, that means, look, that is c equal to nu into lambda, or c by nu, that is equal to lambda. So this gives you lambda dash minus lambda. This lambda dash means the wavelength of the scattered photon, that is the lambda dash, and wavelength of the incident photon, that is equal to lambda. That is equal to h by m0c into 1 minus cos theta, or delta lambda, that is equal to h by m0 into c into 1 minus cos theta. Look, this delta lambda is equal to lambda dash minus lambda. That means there is a shift, or there is a change, or there is an increase in the wavelength of the photon after scattering with the electron. So this shift, that is the delta lambda, is called the Compton shift. Compton shift, and this amount, that is h by m0 c, that is our Compton wavelength or Compton length. So using this equation, Compton is able to explain all this phenomena. So it is fit to this phenomenon. That is, we finally got this equation. That is delta lambda, that is equal to lambda dash minus lambda, is equal to h by m0 into c, that is the Compton length, multiplied by 1 minus cos theta. If you are keeping a detector at the side and taking the intensity of the scattered photon and plot with the incident wavelength, then we will get, the plot is, suppose, look, if this theta, if theta is equal to 0 degree, that means theta is equal to 0 degree means the angle between the incident X-ray and the scattered photon is 0. That means the incident photon is going, after scattering to the electron, going along the positive X direction. That means it is going linearly. At that, what will be the delta lambda? Then what will be the Compton shift? So at theta is equal to 0, delta lambda will be h by m0 into c into 1 minus cos 0. That means h by m0 into c into 0, that is cos 0 1, cos 0 1 minus 1 is equal to 0, that means whole thing is equal to 0. So there will be no Compton shift. That means the Compton shift is depend on not the intensity of the incident radiation, it is depend only on the angle and how much angle is scattered from the incident radiation. This Compton shift is only purely depend on the angle of scattered radiation is equal to 0. So delta lambda, there will be no Compton shift. For theta is equal to 90 degree, delta lambda will be, look, theta is equal to 90 degree, cos 90 is equal to 0. That give you the h by m0 into c, that is the maximum. So that is the maximum shift. That means, and and if you increase this theta, the delta lambda will be decreases gradually. So if you plot this, if you taking a detector in this direction and taking the intensity of the scattered photon and plot it with the incident wavelength, we will get suppose we have a source. Suppose we have a source of X-ray. This is a source of X-ray. The X-ray is coming to this direction. Here is your carbon foil. This is your carbon foil. After carbon foil, suppose it is scattered in this angle. Suppose this angle is theta is equal to 90 degree. And this X-ray source is suppose molybdenum. Molybdenum with lambda is equal to 0.0709 nanometer, and the energy of the obviously photon E gamma is equal to suppose 17.49 kilo electron volt. This angle is 90 degree. We are plotting with the intensity and versus the wavelength. We are getting this kinds of plot. That is, this is the intensity and this is wavelength. We are getting this kinds of peaks. Two peaks is coming at an angle 90 degree. First peak, this lambda, this is wavelength. This first peak coming at lambda is equal to 0.0709 nanometer, and this second peak is coming. Suppose this lambda and this lambda is equal to, I am writing this lambda is equal to 0.0731 nanometer. Look, this first peak is coming at 0.079 nanometer. Exactly same whatever the wavelength of the incident radiation. And second piece coming at lambda is equal to 0.731 nanometer, little bit greater than this data. Obviously, we can tell that this peak is for compound sheet. This peak is for compound sheet. My question is then why this peak is coming? We know that this peak is coming at as this lambda is slightly greater than the lambda of the incident radiation. Then we can surely tell that this peak is due to Compton sheet. But my question is why this peak is coming? This question we will get for our next class, and we are trying to plot in several directions. This is at 90. Look, at different angle. What will be the plot? Suppose that is intensity lambda at theta is equal to 0 degree. This is our wavelength. Look, we are getting a single peak. At theta is equal to suppose 45 degree. We are getting two peak. This is obviously lambda 0. This is obviously lambda s. So little bit sheet. You have plot this x-axis remains same with this. For theta is equal to 90 degree, this plot will be these things. This is your lambda 0, that is wavelength of the incident radiation, and wavelength of the scattered radiation. This is first order wavelength. And for theta is equal to 135 degree. This peak is gradually shifted. So this is the all about the quantum effect. Summary is, what is the summary? What do you learn from the quantum effect? Or summary. Summary. What is the summary? Summary is Compton effect. Compton effect established the particle nature of light. Strongly established the particle nature of light. Again established. Number 2, the Compton shift does not depend on the intensity of the incident radiation. Intensity of the incident radiation, but it depends on the scattered angle. So this is all about the quantum theory. In our next classes we will discuss about the de Broglie wavelength.